Hey everyone, welcome back to my Calculus 2 series. In today's lesson, we're going to be talking about the integral test. So in previous lessons, we learned about a few tests such as the limit test to see whether a series is convergent or divergent. Now, this lesson right here is going to be on a single test called the integral test, and it's basically going to do a similar thing. It's going to tell us whether a series is convergent or divergent, but through a different method. So let's say we had this series 1 over n squared, right? Well, this series is going to be equivalent to 1 over 1 plus the next iteration where n is equal to 2 will be 1 over 4. Next iteration when n is equal to 3, it'll be 1 over 9, and then 1 over 16, and so on. So we can kind of see these little pieces right here, and essentially if we were to analyze a graph of this function right here, we can kind of see how these little pieces that I've marked over here will sort of map out to that. And I'm going to go ahead and pull up a little graph to show you a little more visually. So here's that graph, and the green function represents y equals 1 over x squared. And essentially you could see here that I've drawn out all of these pieces right here. The first little rectangle is the 1 over 1 that we have here. The 1 over 4 is going to be this next piece that we have right here, and so on, 1 over 9 and 1 over 16. Now we have seen images similar to this when we were going through integration, and it's kind of no coincidence that we're going to be talking about this during the integral test. So basically, as you could see, what we want to do is we want to end up summing up these pieces. And well, how can we do that? Again, we're going to use the integral that we've already discussed in previous lessons. So I'm going to take the integral from 1 to infinity, and this is because we don't want to take the integral from 0 to 1. We don't want to take this piece right here. Well, 1, because we know the area, it's just going to be 1, and that's why we're going to add it to the rest of this area. However, it's also because we're going to have kind of like a double improper integral, because as we approach 0 from the right, we're also going to approach infinity. So we kind of want to avoid that. And besides, we already know the area of the leftmost rectangle. It's simply going to be 1. So we have the integral, and obviously we want to integrate the function that we have drawn over here, which is 1 over x squared. If we go on to solve this, I mean, it should be fairly straightforward. We've done plenty of these examples. We're basically going to come to a solution that the area under that is going to equal to 2. And that essentially is going to tell us that the series is convergent because, well, we've hit a finite value. If we were to hit some like infinite value, or we couldn't compute this integral right here, that would mean that the sum of the series would also be incomputable, and therefore we would know that it's divergent. And that is what the integral test is based on. Now I'm going to write a formal definition right now for you, but essentially that's all it is. If we can compute that integral, meaning we can compute the area under that curve, well, then we can also compute the sum of the series, meaning it's going to be convergent. But if we can't compute it, then it's going to be divergent. So here's the formal definition of the integral test. We suppose that we have a function called f, and it's continuous, positive, and decreasing. So these are the three key components to the integral test. We need the function to be positive, continuous, and decreasing. If we see that a of n over here falls under these three criteria, continuous, positive, and decreasing, well then that's a pretty big indicator that perhaps the integral test will help us, and maybe we should spend some time trying to figure it out. So again, we suppose that we have this function, it's continuous, positive, and decreasing on this interval from 1 to infinity, and we already spoke about why it's on that interval, and then we say that, okay, so we let a of n equal to that function evaluated at the nth like coordinate or nth x value, however you want to think about it. Then we say that the series containing that a of n that we just defined to be that function is convergent if and only if the improper integral, this one right here, is convergent. So if the integral from 1 all the way to infinity of that function is convergent, then the series is also going to be convergent. I've kind of written it out here, right here, and then I've written out the opposite right here. If that integral is divergent, well, then the series is also divergent. And this makes complete sense, because if we can compute the integral of that function, well, that means that we can compute the area under that function. And what does that mean? Well, that means that we can compute the sum of all the rectangles that we took under that function. And so that's kind of what the integral test is based off of. So now for this example, we are given this series right here, which is 1 over n to the power of p, and we're asked for what values of p is this series convergent. Automatically, we can see that if p is going to be less than 0, meaning it's going to be some negative value, well, then we can clearly see that the limit of 1 over n to the p would equal to infinity. Basically, the reasoning for that is because 1 over n to p would be negative in this case, and then it would just be n to the p using power laws. We would sort of bring this upwards, and then, well, this, when n is set to go to infinity, then this value will get arbitrarily large, and that limit is basically going to equal infinity. Now we get if p is equal to 0, well, then again, the limit as n approaches infinity of 1 over n to the p is going to equal to 1, because, well, p is going to equal to 0, so 1 over n to the 0 is just like saying 1 over 1, and the limit of 1 is just going to equal to 1. And again, for both of these cases, we're using that limit test, and because it's not equal to 0, we can conclude that for these values of p, this series is going to be convergent. So again, yeah, if you haven't learned about that little limit test that we did in the previous lesson, I suggest you go back, because it's very useful. As you can see, it's very quick and easy to determine if something is divergent. But now, how about for values that are like, for example, well, greater than 1? So let's go ahead and look. Let's define the function to be 1 over x to the p, and then let's try and take the integral. Obviously, the key thing to note about this function is that it is decreasing, it is continuous, and it is positive, meaning it's above the x-axis. So this right here will equal to the limit as t approaches infinity from 1 to t of x to the minus p dx, and I've just kind of brought it upwards using power laws. Now I'm going to go ahead and kind of zoom through the solution, because at this point you should know improper integrals and how to solve them. So I'm going to zoom through the solution, but it will be up once I come back. So when we finish off, we are left at this step right here. And well, what can we notice? We can notice that if p is going to be greater than 1, then the power that t is raised to on the bottom, so p minus 1, is going to be greater than 0, because, well, p is greater than 1. So that would mean that this limit right here, the limit, it would be, sorry, as t approaches infinity of 1 over t p minus 1, well, that would equal to 0, because p would be a positive number, and then obviously we couldn't use power laws and bring t to the top, so we would end up constantly dividing 1 by an even larger and larger number as we continue. So that would mean that we're slowly going to approach 0. So if this were to equal to 0, well, then this up here would equal to 1 minus p, and then obviously the limit of 1 is going to equal to 1. So we're just going to get that it's 0 minus 1. So we're going to have that it's 1 over 1 minus p times minus 1 is going to equal to 1 over p minus 1. And this right here is going to be a constant value, because p is not variable. P we are kind of testing for, but it's actually going to be a constant value. So therefore, if p is going to be greater than 1, then it's going to be convergent. So now we have found when this series is going to be convergent, and yeah, essentially it'll just be when p is going to be greater than 1. Now essentially what we did in that example was we solved for the interval of convergence and divergence of the p series, which is another well-known series that most people end up just kind of remembering. So the p series is just the series of 1 over n to the power of p, and it is convergent when p is going to be greater than 1. And again, the reasoning for that is if p is greater than 1, that would mean that the denominator is going to be getting larger and larger, and that would mean that the fraction itself would be getting smaller and smaller, meaning we would slowly be able to compute the sum of that series. However, if p is going to be less than or equal to 1, well, that would mean that that value is going to be either small or negative, and that would mean that the fraction itself would just keep on getting larger and larger as we continue through the iterations, and then the value would keep on, like the sum of the series would just keep getting larger and larger. So therefore, if P is going to be less than or equal to 1, then it's going to be divergent. So again, this is a pretty popular series, so you should probably know it, memorize it, and kind of just remember its interval of convergence and divergence. So yeah, that's it for this quick little lesson on the integral test. Basically, it was just another way to test if a series was going to be convergent or divergent. Hopefully you guys enjoyed this video and learned something. If this video has helped you out at all, please like and comment as to what it helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I'll catch you guys in another video.